Nick here, M0NTV, and welcome back to my shack and to yet another homebrew video. And today we're going to be launching into building what, well, I suppose you could describe as the brains of this transceiver that I'm going to be building, which is the multifunction digital VFO, variable frequency oscillator. Multifunction because it's going to do a whole load of other stuff as well. And apologies, this turned out to be a huge topic in and of itself, so I split it into two. So the software I'm saving for the next video, and you won't have to wait too long for that, but that will be coming in a week or so down the track from here. But even just the hardware, I mean, this video is way longer really than I wanted it to be, but hey, you know, that's it. It's a multi-function. So I've got a lot of functions to talk about. So yeah, so what we're going to do today is I'm going to show you the built VFO breadboarded and working, and showing you some of the stuff. I'm going to show you then the finished version, and then I'm going to talk you briefly through the wiring diagram and the board layout as well. But just a cautionary word before we dive into this. If you've built digital VFOs before, you should have no worries following this and stand a pretty good chance of getting it to work. If you've never built a digital VFO with a microcontroller and an SI5351 before, I don't think this is an ideal first build. Right? I think it's too complex. So now I have another video about a previous digital VFO, a much more simpler one, which is the one that went into the Shelf 17 rig that I built a while ago. So have a look at that one, and that one uses a lot similar code. It just doesn't have quite as many bells and whistles, and it's simpler to build. And the internet is awash with other designs as well. So what I would say is that if you've never actually launched into that, then start with something a bit more basic, I would advise, before you tackle something which has got more complexity in as this has. If you've never used a microcontroller before, I would say, whoa. All right. Now I feel for you, because this is actually how I started using microcontrollers, was because I wanted to build a digital VFO. But when I started, I soon realised I couldn't do it. I just didn't have the knowledge or the experience, and if something didn't work, I didn't know why it didn't work, and I didn't know how to fix it. So what I did is what I would advise you to do. If you've never messed around with microcontrollers before, that's fine, right? But just pause on your radio construction for a bit and give yourself some time to just go back to the basics and learn how to use it. So in my case, it was an Arduino. So I got an Arduino. There's loads of really excellent tutorials, basic stuff on the internet that you can look at for free and find out how to do it. So, so I'd get an LCD screen or a TFT screen and learn how to wire it up. I'd get a Rotary encoder and learn how to connect that and do simple sketches that actually kind of just illustrate the behaviour and get it to work. And then once I got the confidence, and then I get the SI5351 and do simple things with that. Once I got the confidence for those things, then I could launch into the more complex things. And that's really what I would advise you to do. That it's not that I want to put you off building what I'm about to show you. I'd love people to have a go. But I want you to have the greatest chance of success. And there's nothing worse than trying something and investing all your time and energy into it, and it doesn't work, but you don't know why it doesn't work and how to fix it. I think the moral of the story here is don't run before you can walk. Having said all that, if you're just interested, I hope you find something of interest here, and hope you enjoy. Well, here is my multifunction VFO, and as you can see, just about I've got the Arduino Nano there in the middle of the breadboard. I've got the SI5351 module there on the right, the LCD screen down the bottom left, and the Rotary encoder on the top left. Now, in addition to that, I've got a couple of leads there which are going actually to that speaker, and I've got a couple of leads here going out to 2 switches here as well. And I will fire it up now and show you what it does. Okay, so I've just kind of zoomed in on the screen here. So if I plug it in, you can see the splash screen comes up with the firmware, and then we're on to the main thing. Let's just refocus this. Okay, so now I'm going to show you what some of these different bits and pieces do. So first, most obviously, is the rotary encoder. So at the moment, we're on the 15 meter band, 21.100, and so you can see at the moment in pink, that little 1K, that's I'm tuning in 1 kilohertz increments. And if I press the button on it, which is kind of hard to do with all this paraphernalia here at the moment, 10K, so that I can tune up in 10K or down in 10K increments, 100K, 1 megahertz, which it won't do. And the reason why it won't do that is that that would take you out of band. And when we get to looking at the software, you'll see I've got some protection there to stop you doing that and transmitting out of band. And then it loops back around again. So then that's 1 hertz. Not that you're ever really going to tune to 1 hertz. Precision 10 hertz, 100 hertz, and then back to 1K. Now, let me just move this around for a moment and try and show you some of the other stuff we've got here as well. Yes, so these switches that we've got here, which are just going to, well, one goes to ground and one goes to a pin. And those switches, when they're depressed, will just set the, they'll ground the Arduino pin, basically. And then I've got code that will act on that. So if I go over to this one. Now, you notice that little green dot there. At the moment, I haven't actually got a pin to this. It's just here. But if I ground this, I don't know if I can do this, and you can see at the same time. Look at that green dot. It's gone to red. That's the PTT. Okay? So every time that's grounded, that will turn to red to tell you you're on transmit, and that will, so the whole radio will click into transmit. Now, one of my switches will also, let's see, you see that? We switched to 10 meters. So now we're on the 10 meter band. If I flick it back, there we are. We're back to 15 meters. Now the other switch is for the tuning tone. Now this is why I've connected the speaker up here. So when you're transmitting and you've got the other switch depressed, you'll get just a tuning tone for tuning purposes. So what I'm going to do is I'm going to actually connect the PTT. So that's simulating into transmit mode now. And apologies, this is going to be loud. I'm going to click this. Right, and that will be your tuning tone for tuning purposes. Okay, what else to show you? The other thing that I've got here, I've got two wires that are just kind of out doing nothing at the moment. Those are the two that actually will connect to my switchable bandpass filters. Those give that bias, and you need to watch the last video to understand this. And they will give the bias to actually switch the bandpass filters. And the last thing to say, I think, oh yes, is down here. You'll see I've got a little S meter down here, down the bottom. Now, this is still a work in progress at the moment, but I don't think we can just see. But what I've got here is I've just got a little diode here, and then I've got a resistor and a capacitor to ground. And essentially what this is going to do, this will take a tap off the audio preamp, and it will pass it through that diode there, which will rectify it, so you just get half the waveform, or just the positive waveform, or the negative, depending on how you which way round you put that diode. And this acts as a bit like a kind of sample and hold network. And then essentially we're going to read that voltage in the Arduino, and we're going to use that to give us an S meter reading, and you'll see this when we look at the code. So a bit experimental at the moment, and so that's still a work in progress, and it will need obviously some calibration. Toilet calibration, the SI5351 over here. I'm not going to talk about calibrating it now. You need to go and see the last video that I did on building a VFO when I did the one for the Shelf 17. I'll link the details to that video in the description of this one. Please go and watch that one. I go into detail there about how you calibrate your SI5351 module, which you'll need to do. And you will have a number at the end of that calibration factor, which will go into the code to make sure that you really are on frequency. And speaking of frequency, I've got hooked up here my my tiny SA, and let's just see if I change the tuning increment here for a moment. Right, okay, so you will see. So now at the moment, I've got the tiny SA hooked into clock 0, which is the VFO. Clock 2 is the BFO, the beat frequency oscillator. So that's a fixed amount, a fixed signal level going there, which is going to go into the modulator on transmit and the product detector on receive. So we're on 21, and here, and if I show you now, and what I've got the tuning increment turned to 100k. So you'll see that this is what we're actually reading on the tiny SA from the VFO. This is what the VFO is set to. So remember, we're doing high side injection, and again, go and have a look at the video that I did about designing this rig, when I go into all the details about spectral inversion and all the rest of it. So we're reading a value of 34.328 megahertz, and actually 34.328 megahertz. I'm just reaching over for my calculator here. If we start with the RF, let's just come back over here for a moment so you can see this. So 21, we're doing kilohertz. We're going to take the difference, so it will be minus the VFO frequency, which is 34.328 equals minus 13.328, and that, fortunately, is our IF frequency. And the reason it's minus, again, go and check out that designing the rig back 2-3 videos ago. And tells us that the signal is inverted. So at the IF, we've basically got a lower sideband signal. That's great because we're going to invert it again when we mix it down to audio. So that's not a problem. That's just great. But just to show that, you know, these are not just numbers on the LCD screen. This is actually doing something in reality. If I turn this up 100 kilohertz, so we're going from 34.3 to 8.429. Yes. Now, obviously, the resolution of my tiny SA is, you know, not all that, but you can essentially see. And if I do another 100, so we're on 429. Put up again. 529. Yeah. So you can see we're going up 100 kilohertz, which is what we want to see. So that's what it looks like when it's breadboarded up. I'm going to show you now what it looks like today. And this is what it now looks like. So you can see it's all effectively gone onto this bit of strip board. And the main thing to think is just how small it is. I mean, yeah, I've had, generally speaking, when I built these things, they've had a much larger form factor. But essentially, the whole thing really is just piggybacked onto the back of this TFT screen. So I'll just show you what's what for a minute, and then we'll fire it up. So here are these cables here. Well, first of all, clearly we've got the screen. You can see the SI5351 over here, just here, and over here we've got the rotary encoder. You can see that all wired in. We've got the two switches. That's the switch for the band pass filter, and that's the switch for the tuning tone. And then various wires. So down here, this blue and black, this is the input for the S meter. So that'll be an audio signal tapped off from the audio preamp, which will give us what we're going to need for the S meter, and I'll show you a bit more of that in just a moment. We've got the main 9-volt power supply coming in. This is switching. It's just one ground and two other wires there, which is switching for the different modules. So that's like transmit, power on transmit, power on receive, etc. And we can introduce some delay in when we switch stuff in the software. We've got over here, this is the PTT, and then coming round here, finally, we've got, this wasn't the best idea because they're both green and black wires, but no mind. So this one, I had to label them so I know which is which, this is the bias, which is going to come and switch our band pass filters. We know about that. And this is the actual audio tuning tone. So this is it's a 1 kilohertz square wave, which is coming out from the Arduino. So that's what it looks like. Now, if I just take the screen off for a moment, I just did some headers there. Okay, so I'll take that off. Hopefully, you should be able to see now what's going on. So you can see the Nano here in the middle, and the SI5351. This is the little, there's the diode, the capacitor and the resistor, which is part of that little kind of sample and hold network, and that's a rectifier for the audio signal that's going to be coming in. So essentially, by the time the audio signal has gone through there, you've effectively got DC, basically. There'll be a fair bit of ripple on it, but that's what it is. And it's that DC voltage that will be read then by the
by the Arduino, and that'll enable us to calculate roughly, at least, some indication of the signal strength on our S meter. If I flip it over, you can see there's a fair bit of work here, and you'll see I've had to break the tracks, and in a moment I'll show you the diagram, and you'll be able to download the diagrams that I created, so I would know where to break tracks and where not to. But all pretty compact, really. And I was terrified actually when I powered this up whether it would actually work, because there's an awful lot of potential here to miss something out and get it wrong. But it did, incredibly, which is quite a rare occurrence, I have to say. Right, okay. Well, what I will do then is I will put the screen back and I'll fire it up, and you'll just see that it's working again. And there's one extra thing, because since I breadboarded this actual module, I added just another bit of functionality in the software, and you'll see that. Okay, let's just connect it in now. I know I've got a dedicated 9-volt power in now, but I'm just going to use the 5 volts on the USB connection for now. Okay, so there we go. No, it's not so good, is it? That's better. Now, so all the functionality is exactly as it was before. You know, you can change, you can change the bands, etc. The only thing which is different is the tuning tone. So now you remember when I'm going to switch on this, but if I just put these two wires of the PTT together, you'll see we're in transmit mode now, and that will trigger a whole load of stuff in the code for things that you want to happen when you're on transmit. But there was no indication when you were on transmit, but in tuning mode, and I thought that I ought to do something about that. So let me just switch this switch remote. Okay. So now I switch the tuning tone one. So now if I press the PTT, you see we've got a nice T there, which says, yes, we're on transmit, but we're also transmitting a tuning tone. And, well, I'll tell you what the and is in a minute. But so if I do that, the and is, I'm going to have to try and move this around a bit here, is the tuning tone switch, which is this one here. This one, as you can see, is just your single pole double throw. This one is a double pole double throw, and it's really hard to actually kind of show you here, but essentially what we've got, I've only used half of it, like that, if you can see that, because the other side, so when this is switched, that will switch that in, but it'll also switch the contacts on the other side in, and what that will do is control a relay which is going into the microphone amplifier, and when it's not switched, obviously your microphone will feed into the microphone amplifier, but when it is switched, it will disconnect the mic and connect your tuning tone. So that will, so it will disconnect the mic and it will just put your tuning tone in. So that's what that's going to do. So that's just an extra bit of functionality that I put into it. Okay, one final test I just want to show you. So you'll see I've got the actual the VFO actually wired in now to my regulated 9-volt benchtop power supply, and you see the whole thing is running about 95 milliamps, and obviously most of that is the microcontroller. Now, what I've also got on here is I've got SIGGEN on, and if I just focus this on, hope you can see. So channel 1 on the SIGGEN, I've got a 1 kilohertz sine wave, 4 volts peak to peak. So that's getting near to the top end that you can actually put into the pins of this Nano. They're 5 volts really is the maximum they can do, and I'm going to regulate that down a bit further. Actually, I'm going to take it down to about 4.7 volts. Right, push this here now. Hopefully, if I focus that, you should be able to see now. So you'll see at the minute that 4 volts on the SIGGEN is giving us an S9 output. And this, of course, I mean, no S meter is particularly accurate, but this is, another whole scale of not that accurate. But what I'm basically going for is what you want. So a drop from an S9 signal to an S8 signal, of course, is 6 decibels. Now, when you express that in that's 6 decibels of power, but remember, power is voltage squared over resistance. So actually, what that means is that when you're doing this with the voltage, it's actually half that. So we're on 4 volts at the minute. So actually, a drop from 4 volts down to 2 volts, which is a 3 dB difference in voltage, is actually a 6 dB decrease in power because of how power is calculated. And I'm hoping to just demonstrate this so you can see roughly that it's doing the kind of things we want. We want to know if a signal is roughly 6 dBs higher than the other one. So let's say that we've got an S9 signal there, and we're on 4 volts. And all I'm going to do is I'm just going to half the voltage on the SIGGEN. So I'm going to take the voltage down from 4 volts down to 2 volts, and you watch that S meter, and hopefully, if all is well, it will drop down to. It'll go green and it will drop down because it's only 9. It's only red when it's 9 and 9 plus, but it will drop down to S8 hopefully. Right, there we are. So that's 2. So that's done it. So half the voltage there is the 6 dBs of power that we're seeing reflected there. So if we do it again, so that would be dropping down to 1 volt. So we're on S8 now. So we should drop down to S7. Yep. Now, of course, at the minute, I'm just putting in a perfect sine wave. In reality, there's going to be all kinds of stuff that's being fed in there, and that's a test for another day. But I just wanted to make sure that we're in the right ballpark kind of figure. Okay, so we're on volts. I need to drop down to 500 millivolts here, so bear with me. So we're on S7. We should drop to S6. Yeah, we are. Okay, and so on. Now, full disclosure, once you get to S5 and below, it goes a bit off, and you're not getting that same pattern as we've just seen to the same extent. That may well be because of this diode drop, and I'm using a 1N34A, which has a very low forward voltage drop. It's something like 250 millivolts. And when you think some are about 600, 700, it's very good. So we're not wasting too much signal, but I think that probably when you're looking, I mean, now, we're only putting 500 millivolts in there. Well, 500 millivolts, when you think that, 250 could be being dropped over that that diode, that's obviously going to, and the lower you get, I think that's probably where some of the problems are coming in. But to be completely honest, I don't really care that much. Most of the signals I'm looking at are S5 and over anyway, and it's, you know, it's really just to give an indication of signal strength. And I'm similar at the top, because I just don't have the space, if you like, in terms of the 5 volts that the Arduino will measure to actually ramp up. I mean, most S meters will go 10 dBs over 9 and 20 dBs, and so, well, I can't do that. I'd need a dedicated little chip that would enable me to kind of do that. But I'm trying to do this a bit more simply. So essentially, I've got S9 and then anything over S9. So that's S9 and S9 plus. But anyway, so there we go. So at least in principle, it works. Once I've actually got some of the radio bits together and I'm able to start receiving some signals, of course, then I can recalibrate it. But at least I know it's, we're on the right lines here anyway.
And so here is my, well, it's not really a schematic, is it? Wiring diagram. Let's go with that, which is probably more akin to what you saw when the VFO was on the breadboard. So what to say about this? Well, it's a bit of a mess, but then I think I used pretty much all the pins. There's about a couple of pins that I didn't use, but I've tried to squeeze as much functionality out of that little Nano as I can. And obviously I've gone with the 5 volt wire is the red one, and the black one is the ground, and then I just worked my way through the rainbow, really, which is why the main 9 volt in had to be pink, because I was getting towards the end of the rainbow. Right, so now what to say about this? It does look complicated, but it's not actually as bad as you might think. Part of the rainbow thing is because I wanted to try and make it clear which wire goes to where. Now, all of these connections, although they will crisscross multiple wires, they are, with 3 exceptions, are all point-to-point connections. So in other words, although they might cross, like this yellow one here on D2, although it crosses, 4 wires there, it crosses a wire there, it crosses 2 more there, those are not connections, they're just crossing. The exceptions to this are the 5 volt line, and you'll see we've got a 3-way connection there. That's a real connection. There's a 3-way connection there, a real connection. So I think probably those are the only 2 there on the 5 volt. So both of those are actual real connections. And on the ground, so the ground, you'll see I have multiple 3-way connections on the grounds, and they're all obviously connected together as you would wish your grounds to be. And partly the reason I did it like that was to make the diagram a bit cleaner. So yes, you will have connections on the 5 volt. Yes, you will have multiple ground connections on the black lead. The only other place where you've actually got connections where wires seem to be crossing is down here. This is the little S meter input. So on the Arduino end, the A6 end on this blue wire here of this diode, we've basically just got a resistor, a big resistor, 4.7 megs, and a 100 nanofarad capacitor paralleled with it to ground. So they're just shunted to ground. So these are real connections to ground, and these are real connections to this signal line. Other than that, all the rest of them are just point-to-point connections. Don't worry about the fact I haven't labelled these on the Rotary encoder. On the next diagram you'll see they are labelled, but just in case you're interested, obviously the red here, you can trace it, goes to the 5 volt. The black, of course, is the ground. The white switch, which goes to A3, is the switch. That's when you press the rotary encoder, you get that click, and that will be changing our tuning increment. And then it's my convention, I don't know why I started doing this, but hey, I do. On all of my wiring diagrams, I always have a yellow clock, so this is the clock line, and I have an orange data line. So I've done it here. If you look on the SI5351, there's the SCL, the clock, in yellow. There's the SDA, the data, which is on orange. There are some other orange wires round as well, but that's because I've got a lot of wires here, so sometimes you have to repeat them. Right, okay. On the TFT screen, some of these will have different names. I mean, isn't that just marvellous? As if it's not complicated enough. And I remember agonising over this when I first started wiring these things. I'm thinking, what on earth is this? I think the only one really that's hard to work out is this one that's called A0, which has another name, and you'll see that on the next diagram I show you. And so hopefully you should be able to work out which one goes to where. The others are pretty simple. Clearly these are just bog standard pictures. So I've got the PTT like a switch there, and as we've seen on the tuning tone switch, in reality the switch is a double pole, double throw. So I'm going to have another series of connections which, when you switch this, will not just engage the tuning tone, but will also engage the relay, which will ensure that the tuning tone goes into the microphone amplifier and not the microphone. I think that's probably all to say. Oh, notice I didn't use the signal pins of the SI5351 because I'm using SMAs connected to clock 0 and clock 2. The way this looks is the way it's mounted, i.e. the USB port is facing up. That's really important. I wanted to make sure that I could easily access this USB port. I mean, obviously I don't need it for power because I'm going to feed it 9 volts. This has a regulator on it which will take it down to what it needs, but I'm going to feed it with 9 volts, so that will keep it happy. But it's good to have this because if you want to do any firmware updates, it's easily accessible. You don't want to find out that you've put it in upside down and actually this is pointing down and you've got no room to actually get the cable in. So that's just a little thing. Right, okay, so yeah, so that's pretty much what it looks like on the breadboard. Let me show you now the diagram that took me a bit of time to do, actually, which I had to prepare in some detail before I started actually building the finished thing. And you'll see in a moment what you're going to see resembles very closely what I actually built. And so here is the other diagram that I spoke about. This is really, I suppose we could call this the board layout. So what you're seeing is my approximation of that piece of strip board that I built it on, and you're looking down onto the top of it, but actually what you're doing is you're seeing what's on the top. So you're seeing where we will connect the SI5351, where the Nano will sit, the one row of pins, the second row of pins, and where the LCD screen will connect. And all this wiring, which is all on the top. But you're also, as it were, looking through the board to what's on the bottom of the board. Now these brown bits here are where I've broken the tracks, and you use that little kind of bradawl thing, you know, a couple of turns of it, and you just kind of make a small hole that basically just breaks the copper trace. Now this might be a bit confusing because you might be kind of used to kind of looking at the surface or looking at the bottom of the board, as it were, in which case the whole thing would be backwards. Now, the reason I did this is because I just wanted to make sure that I could fit everything in and I knew where everything was going. So I hope you can kind of follow it. So Essentially, yes, this is the SI5351. I hardwired, I soldered that in, and I soldered in the Nano as well. I could have used header pins. I did use header pins for the TFT screen. Now, the reason that I didn't use header pins for the Nano was basically because of the space, the height of it. I didn't want it protruding too high off the surface of the board, because the screen would then, which is sitting over it like this, would snag on it. I didn't want that. So I would have had to make the screen header pins higher. So it just seemed easier just to solder it in. So I did. I wish I'd waited. Because actually, if you look here, so these breaks in the track, so obviously we're going to want a break there, because we don't want D13 connected to D12. These have got to be completely independent. So you put a break there, which means then if I want to access D13, I can use everything on the left hand side of it. If I want to use D12, I can use everything on the right hand side of it. But you can also use these inner two connections before you get to the break. Right there, they're still both connected equally to D13, and likewise with D12, you can use these two connections as well. And actually, that would have been useful, because there's quite a lot of connections happening around here, and it would have been good to put some there. You can use them if you don't solder the Nano on first, which is what I did. So of course, once you've got the Nano on there, you've had it. You can't access any of these inner ones. You can only use the outer ones. So yeah, note to self: don't be so kind of quick with the soldering iron on this. So it would have been helpful. I could have laid the wires down first and then soldered it in. As it happens, it was fine, but and it turned out fairly neat and fairly small, but it would have been better if I'd been able to do that. So I just tell you that in advance. So what you'd need to do is just to work out exactly where it was. I think the reason why I put the Nano on is because you can see exactly what the number and the designation of each of these pins is, and when you're wiring all these things, it's very easy to get confused. So if you did go the route of not soldering it in, you'd have to put some stickers or something so that you didn't get confused and you knew exactly which one they were. But anyway, that's fine. You've obviously got to break this one here, because you don't want any of this interfering with the pins on your TFT screen. And you can see we got the little S-meter input circuit laid out there. That's fine as well. And it looks much cleaner than the last diagram, because I've got things coming off at different angles, and being able to utilise these horizontal connections gives you more room to manoeuvre, and it's not so confusing as the last one. Not every connection is wired up on the TFT screen. Some of them are no connection, that's fine. And you'll see different designations here as well for some of the pins, so you can compare those with the other ones. These are just two milling holes for me to mount this board on. I won't go into the details of that now. Right, I think that is pretty much everything. All I would say is, if you're going to attempt this, just take it steady. And the old adage of, measure twice and cut once is a really good idea. So, because it's very easy to get confused, and you really don't want to go breaking the wrong track in the wrong place and think, oh no, I meant to do it on that one, or I meant to count 3 and I've only counted 2, because it's a bit of a pig to reconnect them again. So yeah, take your time, and with a fair wind and a bit of concentration, you should be absolutely fine. Well, for those of you that are still watching, congratulations, you made it to the end. Apologies, this is a bit of a long one. It's just one of those huge topics. Apologies as well when I slipped into talking about LCD screens when I meant TFT screens. And just 2 other things to mention: the tuning tone, because the Arduino is producing it is a 5-volt peak-to-peak square wave. That's way too powerful. So what I think I'm going to do is run it through a series of passive low-pass audio filters, which is basically just a resistor and a capacitor. And that'll have two effects. One, it will clean it up, remove a lot of the harmonics, so I'll end up with something more akin to a sine wave. But also it will attenuate it, so I'll end up with a cleaner, smaller signal, which I can then inject into the microphone amplifier. So I'm going to have a play with that. And the other just thing to mention is the VFO output. You perhaps remember when I was showing you the screen of the Tiny SA, it was measuring, well, more than 9 dB. Which is probably a little bit too high. Now, I can't say for definite because I haven't built the mixer yet, but once I've built the mixer, I'll have a play around with that. You can alter the drive level in the software. Well, there's four levels. I've got it set to the middle at the minute, 4 milliamps, but we'll cover that next time. But what you can do is set it to more drive than you need and then just build a 3 resistor pi attenuator on the LO port of your mixer. And I very often do that, and that of course gives you a bit extra kind of matching to 50 ohms as well, which is quite useful. But we'll get to that when we've built some mixers. So I will link below to the wiring diagram and to the board layout, so you can have a look at those, and to the other videos that I referenced as well. And coming along, hopefully in a week or two, will be the next video, part 2, which will cover the software. And I'll make that available then when we get to that. But in the meantime, thank you ever so much for watching. Hope you found something of interest here. And look after yourselves. And I'll see you on the next video. 73. Bye-bye.